with, we will try to recall what we did in the previous session. Thereafter, we will talk about what is Bravais lattices in 3 dimension. Then we will come up to cubic unit cells. Then we will try to do some kind of analysis of cubic unit cells in different aspects of it. Then we will try to define what are unit cell parameters. Then what is atomic packing fraction in case of cubic unit cells. Thereafter, we will try to work out how do we compute density of a solid from the unit cell dimensions, and of course, the lattice type will be required for that. Towards the end, we will try to sum up what we do today. Let us make a beginning by recalling what we did in the previous session. In the previous session, we discussed the ways to represent ordered arrangements in 1 dimension, 2 dimension and 3 dimension in terms of a lattice and things like that. Thereafter, we worked out and explained in detail a differentiation between the meaning of a lattice and the crystal structure. You will recall that lattice is a representation of a 3 dimensional or any ordered arrangement, whereas crystal structure refers to the repeated pattern of the motifs in the crystal. Thereafter, we explained the meaning and the method of identifying the unit cells in a 2-dimensional lattice as well as in 3-dimensional lattice. Thereafter, we described the parameters used for defining the unit cells. This was followed by identifying the relationship between unit cell, space lattice, crystal structure and the crystal, what you see in a microscopic world. So, having done all this, let us now move on to and try to see what are Bravais lattices. We did talk about Bravais lattices in the context of 2-dimensional lattices. Now, we are referring to a 3-dimensional lattice. Now, basically Auguste Bravais in 1848 mathematically showed that there are only 14 distinct ways to arrange points in 3-dimensional space. Now, in other words, means that we can have only 14 lattice types in 3D arrangement. That's all. Basically, if you remember that we said, we made a mention earlier, that is all the crystalline solids which we know of, which they will belong to one of the 7 crystal systems. So, 7 we emphasize that 7 is a very important number there in terms of crystal systems. Now, here from Bravais point of view, there are 14 such lattice types which are possible, wherein we can think of arranging lattice points in 3-dimensional arrangement. Now, there are the 14 Bravais lattices there, but what is important is that these 14 Bravais lattices are divided into 7 groups called as systems. They happen to be cubic, tetragonal, rhombohedral, hexagonal, orthorhombic, monoclinic and triclinic. They are the same ones what we had in case of crystal systems as well. Now, since there are 7 such systems and each one of them will have a primitive unit cell. I am sure that you remember that a primitive unit cell is the one wherein the lattice points are on the corners of the unit cell. So, accordingly there are 7 primitive unit cells, each for each of the systems there. So, that is fine. But you recall that, as I just mentioned, that there are 7 crystal systems, and now we are seeing that there are 7 primitive Bravais lattices, and this gives us an indication that what Hoy proposed, that the outward symmetry of a crystal is a manifestation of internal structure, that stands vindicated. Because what we see is, what Bravais tells us is that in terms of internal structure of the solid, a crystalline solid, we can represent in terms of a lattice, and the lattice can be given in terms of unit cells. So, there are 7 primitive unit cells. What we know in the macroscopic domain is that there are 7 crystal systems. So, there is a 1-to-1 correspondence. In other words, we can say that the external structure of a crystalline solid is a manifestation of a regular internal structure. That is what Hoy said centuries back. So, let us now talk about non-primitive Bravais lattices. So, there are 7 primitive ones, 7 are non-primitive ones. Even these non-primitive Bravais lattices are subdivided further. They belong to 3 types. The first one is called as a body centered one. What it means is that it has an extra lattice point which is at it is centered in the middle of the unit cell. That means, you have all the corners occupied, which basically will be primitive cell, and if you have in addition to the corners being occupied by lattice points, if there is a lattice point in the middle of the unit cell, then we say it is a body centered lattice. Now, what is very important is, before we proceed further, we must make a note of it, that is, to be body centered unit cell, all the lattice points should be the same. That means, all the lattice points which are at the corners as well as at the body center must be identical. Then only we say it is a body centered lattice. Second category is end centered. In this case, what happens is, besides the corners being occupied by lattice points, there is an extra lattice point centered in each of any of the two opposing faces. That means, you can have, suppose you think of a cube, you can have a top bottom face or left right or front back. So, any two opposing faces will have a center there. Okay. So, they are called as end centered. They are further classified as A centered, B centered or C centered, depending on the axis to which the centered faces exist. That means, in this case shown here, what you see is, because this is our A axis, this is our B axis and this is our C axis. So, in this case, what you find is that the face centers are in the on the C axis. So, this is called as a C centered lattice. The next variety is what is called as a face centered. In this case, besides all the corners being occupied, there is an extra lattice point which is centered in all the faces of the unit cell. This is called as a face centered. It is very straightforward. So far, we have seen that there are 14 Bravais lattices, out of which 7 are primitive Bravais lattices and 7 are non-primitive one. And within the non-primitive also, there are 3 different groups there. Now, let us try to see how are these 14 so called lattice systems distributed amongst different kind of lattices. What we see is that there are 7 lattice systems, and say in case of cubic, there are 3 possibilities which are known. One is primitive, one is body centered, one is face centered. Similarly, for tetragonal there are 2 possibilities, hexagonal there is just one, that is a primitive one. Primitive, of course, every group will have, and then there are the different other possibilities. So, if we find out that this adds up to the 14 total Bravais lattices there. So, what you find is that orthorhombic is the one which has got all the 4 variants there. That means, the primitive, body centered, face centered as well as end centered one, whereas cubic has got only 3 variants there. And now on, we will try to focus attention only onto the cubic lattices, because in our curriculum we are supposed to be talking more about the cubic systems and the crystal systems, crystal structures based on cubic lattices. So, we will try to now focus on to the cubic lattices. Now, in terms of unit cells, if you look at that, there are 3 types of unit cells, the cubic unit cells. They happen to be simple cubic, body centered cubic and the face centered cubic. What you see here is that these 3 are shown. I am sure that is very straightforward. This is simple cubic, this is the all 8 corners are occupied, and then this is a body center, and in this case 8 corners are occupied and each face has a centered atom there. What you see is that the body center here and the face centers here have been shown in different color just to make it distinct. Otherwise, they are supposed to be the same. Okay. So, that has to be borne in mind, that in case of pure primitive body simple cubic or body centered cubic and face centered cubic, all lattice points or the atoms occupying those lattice points are equivalent. Now, we take the same picture again, but now in this case we just try to do is we have just shrunken the atom so that we can feel the unit cell better. So, this is a simple cubic cell. You can see it is a cube where all 8 corners are the lattice points there. The body center, similar things are there, and so on and so forth. Now, you may ask a question, when we said that orthorhombic have got all 4 possibilities, whereas for cubic there are only 3 possibilities. Why so? Can't we say that can we have a side centered cubic cell? Let us see there. Now, suppose we think of a C centered cubic cell. So, what will happen is, this is one cubic unit there, cubic unit here. So, this is C centered, so is this one. What you find here is that if we try to create a lattice of this kind, we find that the shaded portion here will form what is called as a tetragonal unit cell there. That means, it is not a new system, it belongs to the tetragonal system. In that case, that means in this case it will not be a cubic system anymore, it will become a tetragonal system. You will recall that when we mentioned earlier, that means a given lattice can have different kind of unit cells. So, out of which the smallest one is normally chosen as the unit cell there. So, in this case it will be a tetragonal unit cell and not a side centered cubic unit cell. Okay. So, there are only 3 possibilities. If we try to have a system of this kind, it will belong to the tetragonal class. Now, let us try to go a little deeper into our cubic unit cells, and if you look at the corner atom, we find that in case of this picture shows you that there are about 8 unit cells shown there as 8 small cubicles there. We find that just for the sake of it, we put one atom here which is part of all the 8 small unit cells there. That means, if I just distribute that, essentially this picture gives you split up portion of that. In this case, what you find that each unit cell there, the small cube here, has 1/8 of the lattice point here. That means, each corner atom or the lattice points is shared by 8 unit cells. So, thereby the contribution of a lattice point or the atom occupying that to a unit cell is 1/8. Similarly, if you look at the edge atom there, so edge atom is shared by 4 unit cells there. So, accordingly the contribution to one unit cell will be 1/4. If you look at the face centered atoms there, face centered atom is shared by 2 neighboring unit cells there. So, whereby the contribution to each unit cell is just half of it. Okay. So, if you look at in a summary of this, if you have a lattice point at the body center that belongs to the unit cell per se, so the contribution is full, just 1. If it is edge center, it is 1/4, face center it is 1/2, for corner it is 1/8. That means, they are the contributions of the lattice points at different positions in the unit cell. Now, on the basis of this, let us try to compute what are lattice points per cubic unit cell. We start with the simplest one, a simple cubic. So, in case of simple cubic unit cell, what you find is we have got only corner atoms there, and we just mentioned earlier that each corner is shared by 8 small unit cells there. So, there are 8 corner lattice points or the atoms which are contributing 1/8 each, and since there are 8 of them contributing 1/8 each, the total comes out to be 1. That means, there is 1 lattice point or 1 atom per cubic unit cell, simple cubic unit cell. If we look into the body centered cubic, we find that in this case there are 8 corner lattice points, each contributing 1/8, and there is 1 atom at the body center. So, that will give me 8 corners into 1/8 plus 1, that makes it 2. That means, the total number of lattice points per body centered cubic unit cell is 2. Similarly, for face centered cubic, if you look at, we find that there are 8 corner lattice points, each contributing 1/8, and there are 6 atoms of the face centers, each one of them is contributing 1/2. So, that will give me a total of 4. That means, 8 into 1/8 plus 6 into 1/2, that adds to 4, which means for simple cubic the lattice points per cubic unit cell is 1, for body centered cubic it is 2, for face centered cubic it is 4. This is very important when we try to talk about the structures and try to talk about the density of unit cells and things like that. These numbers will become important there. So, we have to bear in mind that what is the occupancy, or you can say how many atoms are there per unit cell for the 3 different variants of the cubic unit cells there. Let us move further, and just for sake of it, let us try to define what are the cell parameters, because these terms will come very often to you. The first one is called as the cell edge. Cell edge refers to, suppose we have got a cubic unit cell there. So, this is what is called as the edge. That means, edge of the cube is the so called cell edge in our case here. Now, face diagonal. Face diagonal is, you take any face of the cube, this line here, the line which joins 2 opposing corners of the face is called as the face diagonal. The third term, important term, is your body diagonal. Body diagonal is, that means, if you take a cube, take the, say, any top corner here, say I have taken this one there, the back one, join this with the bottom corner, the opposite side down here, that is called as the body diagonal there. Okay. So, there are 3 things here, and the fourth one is called as the cell volume. Cell volume basically refers to the volume of the cube as such. So, there are 4 things which we will be using very often when we talk about the packing fractions or density and many more things thereafter. So, having talked about cubic unit cells in terms of their appearance and the cell parameters, etc. Let us now talk about the atomic packing fraction of these cubic unit cells. The atomic packing fraction basically refers to the fraction of volume occupied by the atoms or the ions in a crystal structure. What it means is, if I have a cubic lattice or a cubic unit cell, so out of that whole volume, the cell volume we talked about, and that cell volume, what fraction is occupied by the atoms or the molecules or the ions which are there in the unit cell there. Now, we will try to compute the atomic packing fraction for the 3 different variants of cubic unit cells. We start with simple cubic. So, what this picture shows you is that this is a simple cubic unit cell, and out of that I have just taken 2 atoms which are occupying these 2 corners there. So, what it shows is that the middle of this, that is the center of this sphere here and here, this distance here is your edge length here, and this happens to be A, and then this edge length essentially is equal to 2 times the radius of these 2 atoms. So, what it says is the radius of the atom here is the edge length by 2. In other words, which means that R is equal to R, the radius of the atom is equal to A by 2. This is important for us. Why is it important? Let us see. Now, if you know the radius, so we can find out the volume of the atom, that will be 4 by 3 pi r cube. We just substitute R by A by 2 and work it out. It comes out to be 1 by 6 pi A cube, where A is the unit cell parameter there. If we look at the volume of the unit cell, we know that it is a simple cubic system. If edge length is A, the volume is A cube. Now, we can see that the atomic packing fraction will be the ratio of these 2. That means, what is the volume of the atom, what is the volume of the unit cell. If you do that, so it is 1 by 6 pi A cube by A cube, which cancels, A cube gets cancelled. What you get is 1 by 6 pi, which works out to be 0.52, which implies that in case of a simple cubic system, the atomic packing fraction is 52% or 0.52. That means 52% of space is occupied by the atom, rest happens to be void. That means it is not very densely packed system. Let us look at the body centered cubic now. In case of body centered cubic system, what we have shown here is that we have taken this atom belonging to the corner here. This is the body centered atom, and this is the front faced, this corner atom here. So, essentially these 3 atoms are along the body diagonal here. If that be so, we start with, we know that the edge length is A by definition. So, this is my edge length here A, and if I just try to work out face diagonal, I mean this is my face diagonal here, let's see the bottom face here. So, this edge length is A, this is A. So, the face diagonal is root 2A. So, what you see is that I am talking about this bottom face here, this is A, this is A. So, if you try to work out the diagonal of that, that will come out to be root 2A, simple Pythagoras theorem. If this is root 2A, then the body diagonal here, this the white dotted line here. So, this is my root 2A, this is A. So, A square plus root 2A square is 2A square. So, that is 3A square. Take the square root of that, that gives me root 3A. So, body diagonal is root 3A. And what you see is that this body diagonal essentially is equal to, this is one radius, second, third and the fourth one. That means, the radius of the atom happens to be R, then 1, 2, 3, 4R, 4R is equal to root 3A, which is the body diagonal. In other words, we can say that R is equal to root 3A by 4. So, as before, we now compute the volume of an atom. So, which happens to be 4 by 3 pi r cube, and we substitute R by root 3 by 4, what we just computed, root 3A by 4, and we work out, it comes out to be root 3 by 16 pi A cube. Then the volume of 2 atoms now will be twice this amount, that comes out to be root 3 by 8 pi A cube, and the volume of unit cell as before is A cube. So, our atomic packing fraction comes out to be root 3 by 8 pi A cube divided by A cube, which comes out to be root 3 by 8 pi, which works out to be 0.68. That means, the atomic packing fraction of BCC unit cell is 68%. That means, in case of BCC unit cell, body centered cubic unit cell, the packing fraction, that means the volume occupied by atom, is much more as compared to the simple cubic. So, let us now move on to face centered cubic. This picture shows us a face centered cubic unit cell, only part of it. So, the corner atoms are shown as this dotted circles there, and 3 atoms of interest, that is, this is the back top corner, this is the back face bottom corner, the left side, and this is my face center here. So, if I look at this is your face center of the back face here. Now, as before, our edge length happens to be a and the face diagonal happens to be root 2a, because this is my a here, so is this. So, this will be root 2a by simple Pythagoras theorem, and then this, if my radius of an atom happens to be r, we can very comfortably see here that 4r is equal to root 2a. That means 4 times the radius is equal to root 2a, which in turn means that the radius is equal to root 2a by 4 is equal to a by 2 root r. That means basically what we do in all these 3 cases is that we try to find out the relationship between the radius of the atom and the edge length of the cell. So, having done this, again we do the same exercise. We try to compute the volume of an atom, that comes out to be root 2 by 24 pi a cube, just by substituting the value of r to be equal to root 2 a by 4. And now, since in case of FCC lattice, we have got FCC unit cell, we have got 4 atoms per unit cell. So, the volume of 4 atoms will be 4 times this volume, that comes out to be root 2 by 6 pi a cube, and the volume of the cell as before is a cube, that gives me the atomic packing fraction to be equal to root 2 by 6 pi a cube divided by a cube, which comes out to be root 2 by 6 pi, which in turn is equal to 0.74. That means the atomic packing fraction of FCC unit cell is 74%. That means in case of FCC, the packing is much more tighter. That means it is more densely packed as compared to the BCC, which in turn is more densely packed as compared to the simple cubic system. Now, if I just try to quickly sum up about what we have done about cubic unit cells. So, the lattice points per unit cell is 1 in case of simple cubic, 2 in BCC and 4 in FCC, and the coordination numbers are 6, 8 and 12 respectively. We will talk more about it when we talk in detailed structures of in terms of closed packed structures. We will talk about this coordination number again thereafter. And the relationships will be found that in case of simple cubic system, r is equal to a by 2, here it is r is equal to root 3 a by 4, and here r is equal to a by 2 root 2, and the corresponding atomic packing fractions are 52%, 68% and 74%. Let us now do one more exercise here, because this is again very crucial. That is, just by knowing the unit cell dimensions, primarily if I know the edge length, I know other dimensions fairly well, because if I know the edge length, I know the face diagonal. If I know the face diagonal and edge length, I can know the body diagonal. So, it means all the dimensions of the cubic unit cell can be computed just from the edge length. And also if you know the lattice type, so these two informations put together, I can compute the density of the unit cell. Let us see how do we proceed for this. So, let us assume that the edge length of it, which is determined from the X-ray diffraction, to be equal to a units of length of course, and the volume of unit cell will be equal to a cube, which is straightforward because it is a simple cubic system, it is a cubic system. So, volume of cube is length into length into length, or a cube. If I look at the mass of the unit cell, mass of unit cell will be equal to Z into m, where Z happens to be the number of atoms in the unit cell, which could be 1, 2 or 4, as the case may be, depending on whether it is a simple cubic, body centered cubic or face centered cubic unit cell, and m happens to be the mass of one atom. Okay. So, Z into m is the mass of the unit cell, and if we want to basically define density, density is nothing but mass per unit volume. So, the density of the unit cell will be the mass of the unit cell divided by the volume of the unit cell, and we just said that it should be equal to Z into m by a cube, where Z into m is the mass of the unit cell and a cube is the volume of the unit cell. We can do small substitution here, because this mass of an atom can be equated to be equal to the molar mass of the atom or the element divided by the Avogadro number, m by n a. If I do that substitution here, I get the expression as follows, that is, if I substitute for m in terms of capital M, that is a molar mass, and Na, the Avogadro number, I get D to the density to be equal to Z into M by A cube or Z into capital M, that is a molar mass, by A cube Na, which in turn we can simplify as a formula D to be equal to Zm by A cube Na, with the terms have been explained earlier. Now, this is very crucial. The crucial because the density of the unit cell is same as the density of the solid, which is a very important linkages here. Because if I know if I can compute by seeing the unit cell dimension, I compute the density, I can work out, okay, the given solid is going to have so much of density. In other words, suppose I know the density, then I can go backwards and try to compute these parameters there. I can compute Z, that means I can work out what is the nature of unit cell, because density if I can measure from elsewhere and A I get from X-ray diffraction. So, I can compute the value of Z, that means the type of lattice. I can compute the molar mass of the material if I know other things, or even if I know the molar mass, I can even compute Na, the Avogadro number. That means this is a very important expression for us. There are 5 things here, because basically D, Z, M, A and Na. So, knowing any 4 of the 5 parameters in this expression of density, we can compute the 5th one. So, we will find that this expression is very useful. Now, let us sum up what we have done today. What we have done today is we started with reviewing what we did in the previous session. Thereafter, we described different types of Bravais lattices. That means there were 7 Bravais lattices in 3 dimension. Then thereafter, we discussed in detail the cubic unit cells in terms of their location of lattice points, types of lattice points and their contribution to the unit cells. So, this was followed by computing the atomic packing fraction of cubic unit cells. We found that for simple cubic it is about 52%, for body centered cubic it is 68%, and for face centered cubic it happens to be 74%. Face centered cubic is densely packed. Towards the end, we explained a strategy to compute the density of a crystalline solid from the unit cell dimensions and the lattice type. In the next lecture, we will take up close packed structures, wherein we talk about that how do we pack identical spheres in 1 dimension, 2 dimension and 3 dimensions, and what kind of resulting structures come across, because that will be very important to understand the crystal structure of simple solids which we come across. Thank you very much.